We're all set. Daniele, are you all set?
Yeah, I'm here. Yeah. I'm trying to share my screen. Or maybe you can see something.
Yes, we can.
Here, so I will try to write here.
Good. So good afternoon, everyone. Thank you for.
Right. So maybe I hope what I write will go up at some point.
Yeah.
No, later on. Yeah, there's a delay. Yeah.
So good afternoon, everyone. Thank you for coming to this week's edition of the Brazilian Algebraic Geometry Seminar. Today we have Daniele Faenzi from the University of Bourgogne, and he's going to talk about stability of logarithmic tangents. Daniele, please go ahead.
Yes. So thank you very much for the invitation to this, for me, virtual seminar. So I'm very happy to be with you in a way. So, and to have the opportunity to speak about some ongoing work with a virtually Brazilian person. So Simone Marchesi, maybe you know him. This is some work we started in Brazil, so I thought it would be a good idea to you don't understand what I say, or if there's any kind of trouble, so, or at least try to interrupt me, because I could not hear you. I hope I do. Okay, so I'd like to talk a little bit about logarithmic tangents. So let me start by some introduction. So what would I like to study? So I take surface of Pn. So I take a hypersurface which I call D. So which is defined by a polynomial which I call F. Okay. So F is a homogeneous polynomial. So it lies in some coordinate ring which is called R. D, say at least 2 or 3. And so I'm interested in some object which I call the logarithmic tangent sheaf of D. So let me talk about that. So you know that the singularities of D are cut out by the partial derivatives. So maybe all the time K is an algebraically closed field. So mostly C. So you know that the singularities are defined by the Jacobian ideal. So you can, it's generated by the partial derivatives of F. Like that. So I'm interested when D is singular. So maybe let's assume that this is not empty. This will be the key situation. And so you know that this ideal gives rise to a ring, which is sometimes called the Jacobian ring. So this guy here is called the Jacobian ideal of F. And it is generated by these derivatives, which all have degree d minus 1. So you know that this Jacobian ring has been very well studied, and that it gives important properties of D. So I'm actually interested in the first syzygy of this idea. So we have n+1 generators, right, of this ideal. Maybe these have degree. So I have a kernel here, which the tangent of minus log D. Some people write like that. So this is some sheaf here, which you could think, which is called the log, so the logarithmic.
Daniele, Cesar asked in the chat if you are assuming characteristic 0.
Of D. And so in terms of sheaves, so geometrically this is D, so I'm sorry. You mean because you want to see this as a sub-sheaf of the tangent sheaf? Yeah. This guy here is a, oh, okay. Because of the Euler relation, so this goes into the tangent bundle. And here there is what I write like this. So this is the Jacobian ideal, but restrict characteristic of K does not divide D, right? So this guy here, you can see it as a, it's a subsheaf of O D of D minus 1, and you know that OD of D is the normal bundle. It's a slight variation of the normal bundle over the singularities of the divisor. And then this guy here, some people write like this. So there's a shift by 1 in the maybe Cernesi notation or Saito notation. So geometrically, this guy, this sheaf here, its local sections are vector fields which are tangent to the divisor. So in particular, they should go to 0 or the singularities of D. Okay, so vector fields tangent to D. First, I'll give you a couple of properties. So this is the hero. And some properties about the hero are the following. So I'd like to talk about two main features. One of them is freeness. So what about freeness? So in some cases, so it's D is then called free. So this happens for very, very special kinds of divisors. This happens for D's of the form arrangement. So H1 up to HD, where HI's are hyperplanes. So the arrangement, not only D has to be special in the sense that it has to be an arrangement, but also the arrangement has to be special. For instance, so sub example, when the HI's are the reflecting hyperplanes, F is the product of xi minus xj. Okay, so this guy here is called the braid arrangement. It's somehow related to the braid group and so on. So in this case, D will be free. But you see, it must be very, very special. So it's a sub-example of a sub-example of a sub-example. So another case which could be of interest is for discriminant of so this is as simple as you can think. So you take a polynomial, I don't know, sum of xi's in some variable ti, for I from 0 to n, it has a double root if and only if f of x0 up to xn is 0. So f is just proof of a univalue. Then D is free. So somehow this freeness happens. The slogan here is that freeness happens for the most special kind of divisors you can think of. But they need not be reducible. For instance, this discriminant is irreducible, of course, and so to freeness is stability in the sense of stability of vector bundles. So free, so a decomposable vector bundle is almost never free. So it's almost never semi-stable. So we're interested in this opposite behavior, namely sometimes for some the TD is still this notion. Okay, so this happens for when D is smooth. So there's not much to say in this case. It also happens for when D is a hyperplane arrangement. But for the HIs form a generic arrangement, D should be at least n plus 2, I think. So this is already a result of Dolgachev-Karpanov. So you see, D could be quite special, an arrangement, but not too special. So for generic arrangements of enough hyperplanes, this is stable. And it also happens, so another case is when D has isolated singularities of total Tjurina number so strictly below this number here, D minus Q minus 1. So this Q is some integral part of D minus 1 over 3. Well, it doesn't really matter, but some say some cubic function of the degree, and with for n equal 3, so over P3. This is a result of Dimca. So you know this Tjurina number, so you compute the length of the Jacobian ideal. This is just the Tjurina number. Okay. So for P3, if the singularities are not, so they are not too big, then again we have stability. Okay. Right. So these are these two kinds of features that we are interested in, and a third kind of feature maybe I will certainly don't have time to discuss this in detail, but anyway, another feature is when, so the Torelli problem is when does TD determine D? So TD should maybe determine the Jacobian ideal, and then the Jacobian ideal could determine D. So there has been a lot of work about this arrow, so whether the Jacobian ideal determines D. So here there has been work by Ueda and Yoshinaga, again Cernesi, also Wang. So essentially true for singularities which are not of Tom Sebastiani type. And this arrow here was investigated again by Dolgachev and Karpanov. For generic arrangements, so one can be more precise than that, but let us not enter into this now. But of a little bit more hyperplanes than before. And again, it was investigated by Dimca for isolated singularities. If the total Tjurina number, so let me call it tau, is smaller than some function, which is something like this, n-1, d-4 over 2 plus 1, and not Tom Sebastian. Okay, so this is important because when we have this, so when we have both Torelli and the stability, then we can set up some map towards the moduli space of sheaves and so on. So I will try to do this at the end of this talk. Okay, so these are the three features that I'd like to investigate a little bit with you. So let's go. So first theorem, so basic results. So so the first result is a generalization of what Dimca does, but to any dimension and to removing the hypothesis of isolated singularities. So I write S for the codimension of the singular locus. So of course this should be at least 2. I don't like the D to be non-reduced. So the theorem is the following. So I assume that some global sections vanish. So which global sections? I take some exterior powers of our TD. So TD is a sheaf which is, in principle, is not at all a vector bundle. It could have bad non-reflexive locus and so on. So I should double dualize this guy. And I take some Q. This is 0. So I assume this, or again, there's some integral part here coming into play. So D minus 1 P over N. And this P, Q depends on P. And this P goes between 1 and the singular locus, the codimension of the singular locus plus 1. So then it's stable. And okay, so the corollary is that if H0 only of this guy, so this is a little more restrictive Q, so D minus 1 S plus 1 over N. So if this guy is 0, then it is stable. And the further corollary is that if this tau that we had before is smaller than D minus Q minus 1, so D minus 1 to the power N minus 1 with the same Q, the same Q as in the theorem, and so this tau makes sense when the D has isolated singularity. Then again, stability. So this is the first kind of result. So this is a generalization of Dimca's result. So essentially, we remove quite a bit of hypothesis that he has, but that's only because the proof is very much simpler. So we don't somehow we use rather standard techniques. Only in this context they turn out to apply rather in a rather direct way, and so we simplify his proof, and as a bonus we get this kind of generalization. Let me give you a hint of the proof of this kind of result. So sketch of proof. So this is really very intuitive. So let's try to prove the theorem. Take A, maybe a destabilizing subsheaf, whose existence we want to exclude. So you know, the first term class of K, and maybe R is the rank of K. Then we should have that C over R, the slope. So R is not 0 because the sheaf is not 0 and T is torsion free. So this guy should be bigger than the slope of our logarithmic tangent. So the first term class of the logarithmic tangent is this will map to the non-trivially to the R exterior power of this guy. And then we have some reflexive hull. And this guy is just O of C. That should go here. So this guy is not zero and then should be injected, and then H0 of this guy of C should be different from zero. And this is absurd by hypothesis. If the rank is in this range, in the range of P, so for the rank between 1 and S plus 1. So what for higher rank? Sorry, S plus 2. Maybe N minus 1, because N shouldn't take care of it. So then and for higher rank, you should just choose a linear space so linear space L. So I want this linear space to be disjoint from the singular locus. Okay. So this linear space, I take it of codimension S plus 1. Disjoint, sorry, disjoint from the singular locus of D, and maybe also from the locus where the non-locally free locus of the quotient here. So maybe let me write it better than that. So assume L cuts transversally the non-locally free locus of the quotient here, which is torsion free. Sorry, not this guy, but this guy. Okay, then then TD restricted to L actually goes into, so we remove the singular part, so we have this, maybe this one has very big rank, but at least we know that here we have surjective. And this K here, restricted to L, still injects into this guy. And still we have to prove that H0 of this wedge R TD, well, here I don't need this double dual anymore because this guy so restricted to L is 0. But actually here, because we have this resolution, so the dimension dimension I don't know why I'm writing that. Maybe I can say it orally. So here, we have this resolution here. So this resolution implies this. So how to obtain this implication? Well, we just need to observe that to compute the global sections of this guy, you just need to compute the global sections of its dual with a twist. And this dual has no global sections because of this resolution. So this is really a computation. But if I do this computation now, then there will be no time for the extra case that I would like to explain. So, and this is really a computation. So I can tell you more details, but I think this is essentially the idea. So anyway, this is the first kind of result. So actually, I would like to spend the remaining about 20 minutes to on another kind of. So let me pass to the third part of my talk. So this is going to be determinants. So now for this third part, let us go back with our mind to the case of discriminant of binary forms. I told you that that one was free. So a free divisor should have singularities in codimension 1. Okay. So a stable, something will have, let's say, will tend to be stable if the singularities are small. That's some kind of slogan from the previous part of the talk. So we try to look for something intermediate, something with maybe with a very big group of symmetries, like the invariant for a big automorphism group, and something that has big singularities, but not of codimension 1. So it's a little bit higher codimension. So one case we stumbled upon is the determinant. So how to introduce that? Well, let's just take a matrix. So I go back to the notation with R equal to K of x0, xn. So and take M. So I take a matrix of polynomials, n by n. And actually these aij's are linear forms, say. Or R1, they are linear forms. And our f is just the determinant of n. So it has degree n. And so D is a determinantal hypersurface. Okay. So I'd like to ask, what is the behavior of what happens to T of the vanishing of the determinant? So typically, the singular locus, or the vanishing of the singular locus contains the vanishing of the minors of order n minus 1 of n. Okay? So, and typically, this guy, typically it's equal, and typically has codimension 3 in D. So this guy is D, right? So this is, so D could have very high dimension, and the codimension is not 1 as in the free case, but it's 3, so it's big singularity, but somehow singularity under control. So the case where, so the case that we actually treat is when big N is n squared minus 1. So look at, so in this case, there is a standard form that the matrix has, which you all know. So you rename the variables like this. So you have n squared variables. And in this case, this typically is true. Okay, so the singularities are really defined by n minus 1 minors and so on. Okay. Well, anyway, so the kind of result that we have in this case is the following. So oh, just a second. Yeah. So the result is the following. So for this M, so the TD for this choice of M TD is stable, and we have so the resolution is well known with resolution. Okay, so TD, so it has 2 n squared minus 1 generators of degree minus 1, so of degree 1, I'm sorry. And then there are n squared syzygies of degree 1, and then just the minors. Minus. Sorry, here there is an n probably. Yeah. No, this is okay. I'm sorry. And here there's n minus 1. Yeah, this should be fine. So you see, this guy is not free. It has a resolution of 3 steps. So the projective dimension is anyway equal to the codimension of the singularities in D, and TD is really stable. So this is the first point. And the second point is that for X in P big N, so remember that big N is n squared minus 1, a random, so a generic quadric, say that X is isomorphic to P1 cross P1, we have that TD restricted to X is isomorphic to something that we call a principal part sheaf, or a kind of jet bundle. So let's say EM is the kernel of, we take H0, so forms of degree M, and we take the kernel. So I write MM because I'm restricting to P1 cross P1, so this is some kind of obvious notation. So this is the is stable for OM, and 3. Well, so there is there's a third part of the statement. Problem, which I did mention that in the introduction, is that so TD determines D, and actually, so we can now formulate this in a little bit more general or conceptual way. So say to make this fourth statement, I just introduce a little bit of notation. So take okay, so put maybe, I don't know, A is equal to the matrices. So we are working actually with, K degree part 1 of this ring. So our M is actually an element of what? Of A tensor A dual, right? Because M is A1, 1, and so on. More general. Then this Aij will be in A star, R1, as we did before. Okay, so I have a rational map from this A tensor to what? To Rn, which is just the symmetric power n of A dual, the determinant. And this guy goes, of course, to the quotient. So here there is a open part where the determinant is not 0, and GL times GL, well, modulo the center, which is just K star, which operates on the left and on the right as you imagine. So this map here goes to R, and like this. Maybe let me call Dn the image of this map. Okay, so Dn is the image of x n, so it's the determinants. So determinantal hypersurfaces of degree n. Okay. So now, if I look at this part of the diagram here, then so to D, I can associate TD, right? And I told you this guy is stable. So this guy lands into some moduli space. Moduli space of semistable, actually stable. Containing, with having the same term classes or the same Hilbert polynomial as TD. Okay. So we have a map like this, and we call this map phi. From X. Okay. And so the first part of the statement is phi is in a tau 2-to-1 cover over an open piece, an open dense piece of a component of Mn. So dense here means dense in this component. Maybe this Mn has other components which we don't know about, but at least over this component, we get a tau cover over this open piece. And all this has dimension. So it's n square minus 1 square. Okay. So actually this moduli space looks exactly like the set of matrices up to conjugacy. So the set of matrices of linear forms in n square variables up to conjugacy, at least over an open piece. And so what we don't know is how this moduli space, this open piece, compactifies. So this we don't know. Anyway, at least we know this open part. And so I doubt that I can give you a proof of this stuff in 4 minutes, but let me at least go through the statement again. So let me give you this is standard. This is really a direct extrapolation from known results of Lascaux, essentially. The resolution. Stability. So stability follows from 2 and 2 prime imply 1. So implies stability here. our sheaf, restrict as a stable bundle, then it means that the sheaf is stable from the beginning. But then we have to prove 2 and 2 prime. So to prove 2 prime, here we use representations of quivers. Here. Because is, so maybe SL2 cross SL2 homogeneous. And therefore, it has some representation attached to it. And if we prove that the representation is stable, then we prove that the bundle is stable. And we can prove that the representation is stable by working with the representation and looking at its structure and prove that it has no destabilizing sub-representation. So this is a more algebraic. And for 2, actually, maybe the most difficult part is 2 for us. Because, you know, T has, so T is a kernel of a map that goes from n square O to O n minus 1, pretty much as En, but we have to prove that they are the same map somehow. And this is a little bit complicated. So here we use the generations to, so for 2, so to prove 2. Curves actually, plus so something that is called the quadratic Lefschetz property. Okay, and then for 3, and then I will stop. So to prove 3. Namely that PD determines D, actually this is also quite standard. So from the resolution here, from TD recover so the set of matrices of rank 1 so a copy of Pn minus 1 cross Pn minus 1, a copy of this in PB. And then recover D via secants. So if I have the set of rank 1 matrices, I get D as the set of rank n minus 1 matrices just by taking the n minus 1 secant variety. And then, yeah, and then 4 is a little bit longer, but is also, it's based on So on essentially on 3, because 3 proves that phi is injective. Phi so is injective. Very clear that this means that what I mean by that is that phi is set theoretically 2 to 1. Using 3, we can prove that phi is set theoretically 2 to 1, and then plus work of Kleppe and Miroroich to prove it's a submersion. Plus a little bit, a tiny little bit of deformation theory. So just computation of x1. To prove it's actually a local ISO. Okay, so it will be set. So I think I would stop here. I don't know if you people are still there. So
yeah, we are here.
Anyway, that's the end of my talk.
Thank you, Daniele. Are there any questions? So let me ask you something then, Daniele. Is there an estimate of the dimension of the set of 3 determinants? Sorry, not 3 determinants, but 3 hypersurfaces.
Okay, I'm sorry.
Right? So if you take a generic hypersurface in the set of all in the projective space of all hypersurfaces of fixed degree, the generic hypersurface will give you a non-free divisor, right? But do you know estimates of the dimension of the
set of all?
Oh, we couldn't hear you for a while, Daniele.
Yeah. So I hope you guys had a better quality of listening than what I had. So you asked what is the dimension of the set of the determinant surfaces.
No, actually, I asked about the dimension of the set of 3 hypersurfaces.
Do you hear me?
Yes, I do. Hello?
Of 3 hypersurfaces.
Yes.
Marcos, was that you? So you asked what is the dimension of the set of 3 what?
Hypersurfaces.
Yeah, I'm sorry, I don't hear you. I'm so sorry.
Okay, so I'll ask you some other day. Are there, unfortunately, the technical conditions are not perfect today. But are there any other questions?
Yeah, what is unfortunate is that I only hear the word hypersurface.
Yeah. Are there other questions or comments for Daniele?
I'm sorry. So I hope you've heard. Oh, now I hear you. I swear that I'm not eluding the question by pretending that I don't hear. Oh, now he. Okay, so I'm going to stop recording